Hello. In this video, we're going to look at a couple of theorems that will help us factor polynomials, and then we're going to do an example together. So we'll start with the remainder theorem. And the remainder theorem says that when we have a polynomial, p of x, divided by a binomial in the form ax minus b, so a linear binomial, that the remainder is going to be equal to the polynomial at b over a. Now, there's also a sort of a special case of this, and in fact, the one we're going to use most often is if a equals 1. So in other words, I have a binomial in the form x minus b, then the remainder is going to be equal to p evaluated at b. So that's just what happens when a equals 1. So the proof of this, well, recall that for the division p of x divided by ax minus b, we can write that division statement as p of x is equal to the divisor, ax minus b, times whatever the quotient ends up being. Doesn't really matter for our purposes what the quotient is, plus the remainder. And in this case, because we're dividing by a linear binomial, a linear divisor, the remainder is going to be a constant, so just a number. If I'm dividing by something quadratic or something degree 3, then my remainder might end up being an expression of x as well, but here it's just going to be a constant. So let's look at what happens if x is equal to b over a. So if x is equal to b over a, then what I have is p at b over a equals a times b over a minus b times q at b over a plus r, which is just the constant remainder. But look at what happens with the divisor. So a over a, that cancels, and I just have b minus b, which is 0. So now it actually makes no difference what the quotient is. That could be anything, but as soon as I multiply it by 0, I just get 0. So this means that p at b over a is equal to 0 plus r, which is just r. So if I evaluate the original polynomial at b over a, I'm going to end up with the remainder. So that's the proof of that. And we'll come back to how that's useful for factoring polynomials in a couple of minutes. But first, we're also going to look at the factor theorem. Now, the factor theorem says that if a linear binomial, ax minus b, is a factor of a polynomial, then a has to be a factor of the leading coefficient of that polynomial, and b has to be a factor of the constant term of that polynomial. Now, I'm not going to do a formal proof for you, but we are going to look at a bit of a justification with a cube as an example, and hopefully intuitively you can sort of make the extension in your brain to other degrees. So let's say I have a cubic that is in factored form, and it has 3 linear factors in the form ax plus b. So I have a1x plus b1, a2x, oh sorry, I'm going to use minuses for consistency, minus b2, and a3x minus b3. Now, if we want to distribute this, there's going to be a whole lot of distribution going on, but I don't really care about the middle terms. I care about the leading term, so the principal coefficient, and the constant term. So the only way, my leading term here has to be the x cubed term, the cubic term. And the only place that's going to come from is from the product of all 3 of the leading terms of the factors. So in other words, this is going to end up being a1 times a2 times a3 x cubed. And then I'm going to have some quadratic term that comes from various distributions. It's going to involve some a's and some b's. And I'm going to have some linear term that's also going to involve some a's and some b's. It comes from the distribution. But the constant term is only going to come from multiplying together the constants, because any other distribution is going to introduce an x. So when I multiply these 3 constants, I get minus b1, b2, b3. So the original polynomial had a leading coefficient of a1, a2, a3, and a constant term of negative b1, b2, b3. What's important to note here then is that for this leading coefficient, every a value, so every ai, whether that's a1, a2, or 3, has to be a factor of this because it is just all of them multiplied together. And for the constant term, every b value is a factor. And that would be true no matter the degree of the polynomial. When you distribute it all out, the leading coefficient has to be the product of all the leading coefficients, and the constant term has to be the product of all the constant terms. So that's what the factor theorem says. Now, how do these two theorems help me actually factor a polynomial? Well, let's look at an example. So I want to completely factor this cubic polynomial. You learned some techniques for factoring cubes before, factoring by grouping and so on, but this one can't be factored using those techniques. So what we need to do is effectively what we do when factoring numbers if we can't see factors, we just start trying to divide it and see if it works. But the two theorems we've just looked at help me to focus that trial and error process. Starting with the factor theorem. The factor theorem says that if I do have a factor in the form ax minus b, that a has to be a factor of 3 and b has to be a factor of 6. Now, there have to be some negatives in here somewhere because I do end up with negatives in the polynomial. So I always have to consider negatives, but I'm going to just, for consistency's sake, I'm going to assume that my a values are always going to be positive, and then the b values will be positive or negative as necessary. So the factors of 3 are 1 or 3. And the factors of 6 would then be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So what this means is that the only possible factors of this polynomial would be if a1 equals 1, so a equals 1, so I've got x plus or minus 1, x plus or minus 2, x plus or minus 3, or x plus or minus 6. So there are 8 possibilities if the leading coefficient is 1. And then 3x plus or minus 1, 3x plus or minus 2, 3x plus or minus 3, and 3x plus or minus 6. So it looks like at most I have 16 possibilities. But I actually can limit it a little more. Because if I look at these last two, they have common factors. So the 3x plus or minus 3 is actually 3 times x plus or minus 1. And 3x plus or minus 6 is actually 3 times x plus or minus 2. So not only are these factors repeated, but I can actually straight up eliminate these from possibility because they have 3 as a factor. But 3 was not a factor of my original polynomial because negative 17 are not divisible by 3. So because 3 was not a common factor of the original polynomial, it cannot be a common factor of any of the individual linear factors. So I actually only have 12 possibilities. 6, but then with the plus or minus, I multiply by 2. So if I try to divide by all 12 of those and none of them work, then this polynomial is unfactorable. Now I have a couple of possibilities if it is factorable. Maybe there's one linear factor, and then when I divide that out, I get a quadratic that can't be factored any further. Or maybe I do have 3 linear factors. If I do have 3 linear factors, then one of them would have to have a leading coefficient of 3, and the other 2 would have to have a leading coefficient of 1, because 3 times 1 times 1 would really be the only way I could multiply 3 numbers together and get 3. So that's how we use the second theorem, the factor theorem, to limit how many things we have to try. The remainder theorem helps me to actually not have to do the division to see if it's divisible. Because if I try to substitute in the b values, essentially b over a for each of these factors, if I substitute b over a into this polynomial and I don't get 0, then I do not have a factor. Because if it's a factor, the remainder is 0. So let's start with the ones where the leading coefficient is 1, because those are the easiest ones to check. So in the first example, I've got x plus 1, let's say. So that means that b equals, I'm going to start with x minus 1, so b equals 1. So I'm going to see what happens if I substitute 1 into this polynomial. So if I substitute 1 into this polynomial, I've got 3 times 1 cubed minus 4 times 1 squared minus 17 times 1 plus 6, and I get negative 12. So that one is not a factor because it has a remainder of negative 12. If I substitute negative 1 now in, I end up with 16, so also not a factor. So let's move on to the x plus or minus 2. I'm going to substitute what if x equals 2. So p at 2, I get negative 20, also not a factor. And if I substitute in negative 2, then I get 0. So p at negative 2 equals 0. So great, we've identified a factor. This means that x plus 2 is a factor. So as soon as I identify a factor, then I divide it out. So this is like having the divisibility rules for numbers. If I can add all the digits of a number together and see that it equals 9, then I know that number is divisible by 9. Once I know that, I divide out the 9. Same thing here. I now know that this polynomial is divisible by x plus 2, so I'm going to divide it out. And I will use synthetic division to do that. So the coefficients here are 3, -4, -17, 6. I'm going to stick a -2 out front here. So 3, -6, -10, I get 20. This gives me 3, -6, a remainder of 0, which I already knew I was going to have because I knew this was a factor. So this means that I have the factors x plus 2 and 3x squared minus 10x plus 3. At this point, I have a quadratic, so we have a lot of techniques for factoring quadratics. I could actually use the factor theorem and the remainder theorem again, but that's a bit of a waste of time here because I can factor this one just by inspection. I get 3x minus 1 times x minus 3. So those are the 3 linear factors. What that tells me is if I had tried to evaluate p at 3, I also would have gotten a 0. Or if I had done p at 1/3, I would have gotten a 0. But I didn't have to find all of those that way. I found one of them and then divided it out.